So we have an interesting question here, which is given an LSTM layer, right? Given an LSTM layer, how many parameters does the LSTM layer contain? Not just one LSTM unit, but an LSTM layer, right? So let's assume we have an LSTM layer, right, in a recurrent neural network with, let's say, M units, right? We have M units in the layer, which basically means that we have a layer, right? Let's assume this is our input, right? From our input, we have a layer, right? Again, each of them is a recurrent activation unit, right? In this layer, let's assume there are M units. Of course, the output from the M units will go to the next layer, obviously. There will be a next layer, maybe a dense layer or something like that. But let's focus on this layer, right? This is an LSTM layer with M units, unit 1, unit 2, unit 3, unit 4, so on, unit M, right? So let's assume we have M units. Now the question here is, given an LSTM layer, so what I mean by layer is this whole layer, right? Given an LSTM layer with M units, how many parameters does this contain? Very interesting question. We actually use the final formula in one of our videos, but I'll derive it here carefully, right? So let's go and understand it from the perspective of a single LSTM unit. And by the way, we went through each of these diagrams when we learned about what an LSTM here is, right? So LSTM has a forget gate. LSTM in a nutshell, right? If you look at it, overall your LSTM basically is like this, right? This is what your LSTM looks like, right? It has the 4 gates. This is gate 1, gate 2, gate 3, and gate 4, right? So now let's look at the formula for each of the gates, right? And from that we'll derive what all parameters do we have. Okay, let's start this. This is our first gate, right? This is our first gate. For the first gate, we are applying a sigmoid function on WF multiplied by HT minus 1 XT plus BF, right? This is what we are employing. Again, you can see this gate explicitly marked here. This gate takes input as HT minus 1 and XT. This is the input at time t. This is the value of the hidden layers from time t minus 1, right? Now these two go into it, and of course I have a bias term BF, right? This whole equation here is like W transpose X plus B, right? I mean, this whole thing, if you call it as X, this is W dot X plus B. This is the bias term. Now let's look at how many parameters do we have in this, right? Of course, this is one parameter because this is a scalar. Let's assume our input vector, right? Our input vector, let's say, is n dimensional. We often use d-dimensional, but in lot of papers which use LSTM derivation for number of parameters, they use n. So just for consistency, let's say that xt is an n-dimensional vector, right? Very important here. Instead of saying d-dimensional, I'm using n-dimensional here. And now these two are very clear, right? This is a scalar and this is a vector of size n. Now comes the question, what is this? What is the size of ht minus 1? Right? This is a very important question. So the size of ht minus 1, let's take our ht minus 1. This is basically your hidden, this is the values of the hidden units from the previous time step, right? And if you look at it, our model has m units, right? So the size of the hidden units from the previous time step would be equal to m, which is nothing but the number of units. Because the values of all the hidden units from the previous time step will be input to each of these. This is very important. Remember, in this diagram, we are only seeing one LSTM. If you look at any of this diagram, right, we are seeing one LSTM over time, right? If you look at any of these diagrams, let me just pull it up, right? If you look at this is basically one LSTM cell across time. This is xt minus 1, xt plus 1. But if you have an LSTM layer with multiple LSTMs, right, you have m LSTM cells here in this layer, and there is also a time axis, right? This is very important not to get confused. The time axis is different from the number of units we have. So if you have m units, the size of your hidden units, right? Because how many such hidden units exist? M such hidden units, because you have an M layered, or you have a layer with M units, right? So now if you go back to the original formula here, from now things will become fairly straightforward, right? The size of this is 1, the size of this is, let's say, n, the size of this is same as the number of hidden, it's the same as the number of units in your layer. Your layer has m units, right? So the size of the previous timestamp hidden units from all the m units, so this will be m. Now what are the unknowns here? See, this is coming from the previous layer, right? xt is the input from the current timestamp, not layer, from the previous timestamp, right? Now the unknowns in this are your wf and bf, right? Those are the two parameters that you have to find in your LSTM, right? You will apply stochastic gradient descent to determine your wf and bf. Those are the two parameters. Now bf is of size 1, that we already know. What is the dimensionality of wf? See, wf is a vector that is being multiplied with a concatenation. Remember, this is a concatenation. This is a concatenation between these two vectors. So this final vector is of size m plus n. If this is of size m plus n, this vector also should be of size m plus n. Simple here, nothing very complex. Now the two parameters for the forget gate. Now, this is only one gate, remember. For one gate, this is the unknown and this is the unknown, or these are the parameters that we have to determine. The size of this is 1, the size of this is n plus m, where m is the number of units in the layer and n is the dimensionality of your data point xt. Just to be very clear here, n here is not, it is not the number of data points. Let's be very, very clear here. N is the dimensionality of xt. This m basically comes from the fact that we have m units, m LSTM units in these layers, and all the outputs from the previous states are input to this unit, right? So now for one gate, how many parameters do we have? N plus m plus 1. This is for one cell. Look at it. We are all looking at only one cell's perspective. For one cell, for only one gate. This is only one gate. One cell, one gate, we have n plus m plus 1 parameters. Okay, let's remember that. Okay, let's write it down. So for one cell, for one LSTM cell, right? For one gate, we have n plus m plus 1 units or parameters. Not units. N plus m plus 1 unknowns are parameters that you have to determine. Now, just like this, just like your FT, there are 4 gates. This is your forget gate, right? You have 4 gates, right? Look at this. This is your second gate, which has Wi and Bi. Now, Wi is also n plus m size, because again it has ht minus 1 and xt. This is also size 1. Similarly, you have C hat, your C. C again has WC and BC. This is again n plus m sized vector, and this is a scalar of size 1, because again this is getting multiplied with ht minus 1 concatenation xt. So your wi and bi, right? So you have, so the first gate, so this also has n plus m plus 1. This also has n plus m plus 1. Parameters are unknowns, right? We have seen 3 gates till now, right? The first gate we have seen, which has n plus m plus 1. The second gate, the third gate. Again, this final gate is basically just a operation on top of existing values. And then you have your final value. This again has your W0 and B0. Again, this is n plus m and this is your 1. So in total, we have 4 gates. We have 4 gates, right? We have seen this, right? If you look at all the formulae, right? All the formulae here, you have one gate here, you have one here, right? You have your second gate equations here, you have your third gate equations here, the fourth gate equations here. So you have 4 gates. Again, we are talking only about one cell. One cell, one gate has n plus m plus 1. All the 4 gates, each of them has n plus m plus 1. So this will become 4 into n plus m plus 1 parameters, right? Again, this is all with respect to only one cell. But our layer, remember, our layer consists of m cells or m units. That's what we said, right? We have m units or m cells. I use the word unit and cell interchangeably. because it's also called as an LSTM cell or an LSTM unit. It's basically the same thing. Now when I have m cells, so one cell has 4 into n plus 1 parameters. So m cells will have m into 4 into n plus m plus 1 parameters, which is equal to 4 times nm plus m square plus m parameters. So these are the total number of parameters. These are the total number of parameters that you have in an LSTM unit, or in an LSTM layer, not a unit, sorry, in an LSTM layer with m cells. Right? Let's look at a simple example. There is a very nice example that I came across. Okay, let me look it up. Okay, all this is slightly complicated. There is a very nice question that was asked. So let me just Google search for it. LSTM number of parameters. Actually, there are many answers for this, but none of them very convincing, and it takes a little while for you to get used to it, frankly speaking. Right? So let's look at it. Okay, let's look at this. This is a very interesting example, right? This is actually a question on Stack Overflow. Here, the question here asks that I've created an LSTM layer, right? Look at this. This is an LSTM layer with 256 units, and my input dimension is 4096, right? And my input length is 16, right? So my dimensionality of input, so this is my n. I have 256 units in my layer. This is one layer. This is one LSTM layer which has 256 units. So this is my m. My input dimensionality, or the dimensionality of my input vector, is n, right? Now let's look it up. So so here, if you look at it, if you do in Keras, if you look at the number of parameters, it says this has 4.457 million roughly. These are the number of parameters. Now how do we arrive at this number? Now let's look at the answer. Very simple, very well explained answer. So if you take 4 into, right, what is the formula that we came across? 4 into nm plus m square plus m. So this is 4 into, right, this is m into, this is your n, this is your m, this is your m square, right? These are the number of parameters. But here you might say, why did this one not exist? Why don't we see this m here? That's because here we have bias terms. If you look at our formulation, right? If you look at our formulation, in this formulation we have bias terms. If the bias term is present, then you will have this plus m. If the bias, this is very important. This term will exist if and only if there are bias terms in your equation. If your equation does not have bias terms, then you will not have it. So in this, there are no bias terms, and what you have here is 4 into nm plus m square. You don't have the plus m because there are no bias terms here. In the default Keras thing, there is no bias term, but you can add a bias term and you'll get a slightly different value. I hope the additional one comes from the bias. Again, here he explains the person who has answered Markin here explains the whole thing. But I hope this question is clear now on the number of parameters that we have. Again, this plus m will only exist if you have bias term, or else you won't have it. Okay, very simple. So this formula I hope is clearer to everyone now.